Hi everyone. Okay, so I had some technical difficulties with the previous method that I was using, so hopefully this is gonna work. So I had told you all that I would be working on the lecture for two-sample hypothesis testing, and so today we are going to do that, and we are also going to get into next week's lecture, which is going to be chi-square. So like I had mentioned the other day, I'm feeling a bit under the weather. I still am. Whatever the cold front blew in is definitely not treating me well. So I'm going to work through these for you using this method, so you aren't forced to see my sickly looking self. Okay, so if we remember last week and the week before, we talked about single sample hypothesis testing with sigma known and sigma unknown. And we remembered that these were very similar processes, save for having to estimate the standard error and using T or Z versus Z. So for hypothesis testing with two samples, we're going to kind of expand upon the logic that we talked about last week and the week before. So instead of working, and if you hear somebody whining in the background, that's my brat, one of my brats, Cooper, who is being very whiny. Hopefully they'll behave themselves. So instead of working with single sample research questions, we're now going to be working with situations that involve two samples. So a lot of times we might refer to these two sample tests as difference of means tests. And so of course it's going to be a situation where we gather information from the sample and want to generalize it to the population, right? Remember, that's going to always be our ultimate goal, is taking the information from the sample and generalizing it to the population. So in this case, it's going to be two populations and two samples, right? Hence the name two-sample hypothesis testing. And so we've already talked kind of about the process, about how to go through hypothesis testing, right? Where we state the null hypothesis, so we're going to be doing that same sort of thing. But we're going to be stating it slightly differently in two-sample hypothesis testing. But, you know, then we will identify our critical value, right? Perform the test, and then we'll draw our conclusion, right? Just like we kind of talked about last week with making note to type 1 error if we reject the null hypothesis, and so on and so forth. I'll move my fat, nasty hand out of the way, sorry. And I cut my thumb last night because apparently I think I'm Chef Ramsay in the kitchen. Okay. So I believe I had mentioned this before, but situations involving two-sample hypothesis tests are either going to be situations where the samples are matched, or sometimes you hear it referred to as like a paired samples test, or independent. So of course, first we'll be talking about the matched samples t-test, or the paired samples t-test. And so to say that two samples are matched or are paired in some way, it's... Cooper, stop. Sorry. Let me get some water, sorry. But I can continue talking because that's how we're doing it. So, to say that samples are matched or paired, sometimes you hear them called related samples. Basically it means that these samples were not drawn independently of one another. So, one example example might be like if you have maybe like married couples or something, and you ask, you know, not to be heteronormative, but just to demonstrate, like if you ask husbands about certain things and you ask the wife the same questions and then you compare their answers, that would be an example of a matched sample or a paired sample. Probably the most common example of a matched sample test or paired sample that you'll come across is like a pre-test, post-test type situation. So like if we think about, remember how at the beginning of this semester we gave you the pre-test, and then so like basically the way like the pre-test post-test works is like, you know, you test people at like time 1, and then there's an intervention, whatever it might be. We'll talk more about that in a minute. And then you test them again at time 2, and you compare the results from time 1 to time 2. And, you know, it's the same people being tested both times, but so that's why it's a matched sample or a paired sample. They're basically being tested against themselves. The same people are measured twice, basically. Okay, so let's look at now, sorry, my water splashed, of course. Let's look now at an example. So let's say that we had, this is kind of a stupid example, but it's kind of good because it really kind of demonstrates exactly like the logic of a matched sample or a paired sample t-test. Okay, so let's say that we let's say that we had 15 participants, and we wanted to get information from them in like a before and after test situation where we were looking at their drug awareness. Again, this is a stupid example, but it's good because it will help us, you know, do what we need to do. So let's say that we collected the following information from 15 subjects. Okay, so subjects, and let's hope this fits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That looks so bad. Okay, I'm gonna do it on a different page. Sorry. Okay. Subjects. Normally I would have this like projected on the board for you or something. 1, 2, 3, 4, much better. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, perfect. So let's say we have our subjects, then we administer the test. So we call that T1, so like test 1 or time 1. And we get the following results. 50, 77, 67, 94, 64, 77, 85, 52, 81, 91, 52, 61, 83, 66, and 71. Okay, so we give them the test, we record their scores at time 1 or test 1. We then have the intervention. So in this example, it's like we show them a video about the dangers of drugs, which again is a stupid example, but whatever. We then measure them at time 2 and we record their scores, which were as follows: 55, 79, 82, 90, 64, 83, 80, 55, 79, 91, 61, 77, 83, 70, and 75. Okay, so what we're going to be looking at is the difference between time 1 and time 2, right? And always remember, we're not just interested in the difference, we're interested in determining whether or not that difference is significant. And through using the t-test, through using this test, we're able to. So we can glance at, this data and say like, okay, well, it looks like it's different, but let us please actually go through and find the difference. So we'll take time 2 minus time 1, and we get 5, 2, 15, negative 4, 0, 6, negative 5, 3, negative 2, 0, 9, 16, 0, 4, and 4. So we're interested, I hope this pen doesn't give out. We're interested in the differences, right? They could be positive, negative, or 0, as we see. Okay? So, in order to kind of determine some things, some ingredients that we're going to need, we are going to basically find the mean of the differences. So this is kind of something that we've done before. So of course we know if we want to do that, we're going to add up, right, all of the differences. We're going to sum D, which sounds silly. So if we go through and add that up, 5 plus 2 plus 15 plus negative 4 plus 0 plus 6 plus negative 5 plus 3 plus negative 2 plus 0 plus 9 plus 16 plus 0 plus 4 plus 4, we get a sum of the differences equal to 53. So sum of the differences is equal to 53. Then of course, when we're finding the mean, we'll divide by n. So 53 divided by, what am I doing? Divided by 15. 53 divided by 15 gives us a figure of 3.533, repeating. Okay. So the mean of the differences is signified as d bar. So d bar is equal to 3.53. So we're in a position to say the mean of our sample differences is 3.53. Okay, so not too bad, kind of working through doing some things that we have already done. Now, just as we can calculate the mean of the differences, we could also calculate the standard deviation of the differences, and we would do so, and that's indicated as S sub D, we would do so by taking the square root of the sum of D minus D bar squared divided by n minus 1 and taking the square root of that. Okay, so it would, if we remember back to, I'm going to turn on this light. If we remember back to the formula for calculating the standard deviation, we'll remember it's literally taking, in the standard deviation, just a regular formula, it's x minus x bar, but here it's d minus d bar, right? And we could go through and do all of that. I'm not going to belabor it. I'm not going to make you do that. Oftentimes I'll give you the standard deviation of the differences. But if we were to actually go through and do all that, our sum of d minus d bar squared would be 525.72. We would divide by n minus 1, so 15 minus 1. So the square root of 525.72 divided by 14. Let's go down here because clearly I don't know how to ration my space. That would be the square root of 37.55. So our final value for the standard deviation of the difference of the means is 6.13, right? So having our d bar equal to 3.53 and our standard deviation equal to 6.13, we're actually in, a situation where we have quite a lot of information. So if we want to, kind of take a moment to focus on what, please don't chew on that. Golly, these dogs are driving me mad. He's got a toy that he's chewing on, but also chewing on the box that the toys stay in. I just can't. Okay. So if we think about what we've done thus far, we've taken a sample of 15 people. We've noted their scores at time 1 and time 2. We calculated the difference between the scores. We calculated the mean of the difference between the scores. And we calculated the standard deviation of the scores. Now, of course, when we're moving into thinking about the null hypothesis, basically, if we remember that null hypothesis, depending on what we're doing, is going to either be a statement of no difference or equality or no relationship, right? Depending on what it is we're actually doing. So basically, if we're thinking about the mean difference between time 1 and time 2, then our null hypothesis would be that we expect the mean difference in the population to be equal to 0, right? No difference. That's basically what we're saying. No difference. Sorry, that looks bad. So whenever you are writing your null hypothesis for paired sample or matched sample or related sample t-tests, your null hypothesis is going to be mu sub d bar is equal to 0, right? The mean of the differences that we got from subtracting the score at one time from the score at another time. Now, something else that we have to bring into account is the standard error of the mean difference, which is symbolized as S sub d bar. So S sub d bar is the standard error of mean difference, and it is calculated by taking our standard deviation divided by the square root of n. This should not be a shocker because we know this is how we get our standard error for our other examples. Okay, so if we recall, we calculated or were given our standard deviation value of 6.13, and we're dividing it by the square root of n, which we know is 15. Okay, so that gives us 6.13 divided by 3.87, which gives us a standard error of the mean difference equal to 1.58. So again, using all of these different ingredients that we have and thinking back to some of the things that we've done in the past. Okay, now we've got all of the ingredients that we need to apply the test, okay? So basically, we are going to compare our observed mean difference to the assumed mean difference of 0 and divide the result by our estimate of the standard error, which then gives us a t-value, okay? So the calculation for the t-value is as follows. T is equal to d bar minus mu sub d bar divided by s sub d bar. Now, if we assume that mu sub d bar is equal to 0, then we can just drop that from the equation. And so t will be equal to d bar over s sub d bar. So in our present example, d bar was equal to 3.53. S sub d bar was equal to 1.58. And when we calculate that, we're left with a calculated test statistic, Titus, U2, equal to 2.23. Okay, so we've arrived at a t-value or a t-ratio of 2.23. Now, all that's left to do is compare our calculated value with a critical value. So let's say that we had set our alpha level at 0.05. Just like before, our degrees of freedom are going to be equal to n minus 1. So in this case, our degrees of freedom are equal to 15 minus 1, or 14. So please recall that we will consult Appendix B, wherein we find the intersection of our 0.05 level of significance with 14 degrees of freedom. So we're left with a t critical of 2.145. So t critical equals 2.145. So we know that in this present example, our calculated value is greater than our critical value. And as such, we can reject the null hypothesis. Remember, with the knowledge that 5% of the time, or 5 times out of 100, we've committed a type 1 error, right? So whenever we reject the null hypothesis, we always have to make sure that we include that information. Okay, so I'm going to give you some examples or some practice that you can work through on your own before I move on to independent sample t-tests. Okay, so let's say, okay, assume match samples, each involving 10 cases. Okay, so n equals 10. And the following information, you have a d bar equal to 2.10. You have a standard error equal to 0.61. So set or state the null hypothesis. Assume an alpha of 0.05. Calculate t. And draw a conclusion. Man, this notepad that I have is kind of crappy. I got it for myself at Walmart. I'll get some better ones at school. I think I might be headed up there tomorrow. Okay. Next, why don't you assume 2 match samples, each involving 19 subjects or people. Oh, you're not gonna like this one, but you gotta do it. Assume that you have, well, actually it's not that bad. Okay, you have 19 subjects, You have a mean of the differences equal to 7.11. You have a standard deviation of the differences equal to 13.84. So you're going to have to calculate S sub D bar, but don't fret, I told you how to do it already. Assume an alpha of 0.05 and do that same thing for this set of numbers. So do that, and then we will regroup in a minute after you do this and talk about independent samples.